Welcome to EET3329C Communication Systems at Valencia College for the fall semester of 2020. This is your instructor, Dr. Wilfredo Rivas Torres. Today we will continue Lecture 2, this is part 2 of Lecture 2, where we've been talking about signals and signal space. So I intend to cover the topics of orthogonal signals, correlation of signals, Parseval's theorem, and then trigonometric and exponential Fourier series today. Let's get started. So we first will talk about signal decomposition and signal components. So let's say we want to take a real signal and we want to sort of approximate it with another signal, right? So what we want to do is we want to take any signal g of t and we want to approximate it with another signal x of t, right? So that's what we kind of want to do. And that's what we see here in this first expression, g of t approximately c of t. Okay. Um, and so this is the function that we want to approximate. And we want to do that with over the interval between t1 and t2. So in order for us to do that, why don't we establish an error, right? There needs to be a way for us to begin to quantify how good our approximation is. And we come up with an error function, right? E of t. Now, E of t is nothing but our real function minus our approximate, right? And if our approximate function were really, really good, this number would be very close to zero, right? But if you remember back our discussion on vectors, we have a vector for g of t and our approximate function, and that's a lot of samples or a lot of points for us to calculate error. Wouldn't it be nice if we had just one way to size our error? Remember we talked about signal size. So error is a function. So we can actually calculate its energy, right? So why don't we try to minimize the error by minimizing the signal energy in the error we will call capital E sub E, right? And all of this, remember, within the interval between T1 and T2. So basic definition of the energy of the signal, we do the integral of the square, right? That's what this expression here is. And it can be shown that you can minimize the error uh, or the energy of the signal error in this approximation if you use a C value equal to this expression here, this ratio of these two integrals. Now, it looks a little bit intimidating as an expression, but we immediately recognize the denominator as the energy of the function that we're using to approximate x of t, right? So immediately we know that this is the energy of that signal, so that's 1 over ex times the integral of the product of the two signals. Okay, and this is quite a remarkable thing, right? So if I want to approximate a signal one by the other, and all I have is the one control, right? C is constant C. This is what I need to determine in order to minimize that error. And let's look at an example, okay? So here's the example. And what we want to do is we want to take a g of t and approximate it by c times sine of t. Now our g of t is the square wave here, right, in this picture. So it's 1 between 0 and pi and minus 1 between pi and 2 pi, okay? So t1 is 0 and t2 is 2 pi, okay? So we want to figure out, in this case, the energy of x of t, which is sine t, is nothing but the integral of sine squared. And if you do that integral, you come up with a value of pi. So when we want to calculate c, 1 over ex was 1 over pi, and this is the product of the two functions. Right, now g of t is defined between 0 and pi, so it's not a continuous function, it's discontinuous. So we evaluate it as 1 between 0 and pi and as minus 1 between pi and 2 pi, so that's why you have the integral gets broken in two, and you can see, well, this is 1 times sine and this is minus 1 times sine. And if you do the whole integral, you end up with 4 over pi. Now, let me try to see if I can get my pen to work today. And if I could get my pen to work today, if you go, this is an interesting problem to do in Octave or MATLAB. You end up with, if I had a scale, I could do a plot, right? Could do a plot, and let me try that again. If I could do a plot, right? My x-axis for some reason wants to do this really long line. But if I did that, I would end up with some kind of a parabola like this. Okay, if you can imagine that. And then this would be pi over 4, which would be my minimum point here. Okay, and then you end up at either side. Let's say this is pi over 3, and on the other side, let's say this is pi over 5. Oh, I should have done that the other way. This is pi over 5, which is a smaller number, and pi over 3, which is a larger number. And you would see that always, right, you get this parabola, but pi over 4 should be your minimum number. And what you have here is, this is would be E, or your error, right, squared, and then this would be C. If you do that, you should get some kind of parabola that looks like that. And I apologize, my tablet's really acting weird today. All right, so let's talk about orthogonal signals. So um, we can say that if you have a component of a signal g of t of the form x of t, and if that equals 0, right, that component, what we're actually saying is that the c that we were saying above when we're trying to approximate, if that is 0, then g of t and x of t are orthogonal to each other within that interval. Quite interesting. Um, if you think about this as vectors, and let me see if my pen can will collaborate a little bit with us. Um, this is very simple, but let's see. Let's say I have a vector, right? I'm going to try to draw a vector here. Every time I draw a horizontal line, I don't know why my pen does that. But let's say I have a vector, and I'm going to call it G. And I want to see a vector X, right? This is my vector X. So I can say that X equals the magnitude of G times the cosine of theta, right? Where this angle here is theta, okay? Now, if I had a G prime, right? Let's call this G prime, and an angle theta, theta prime, right? Then when I try to calculate, let's call it X prime, right? The vector along the X axis, it comes out to that because cosine this theta prime is 90 degrees, that because of that cosine of 90 degrees is 0, and 0 times whatever magnitude G prime has, so X prime would always be 0. And you can see that X prime and G prime would be orthogonal, or 90 degrees to each other. And that's pretty much the concept that we mean with these orthogonal signals. Okay. Again, I want to mention that this all happens over the interval from T1, right? From T1 to T2. Okay. And I am very sorry about all those lines, so let me put the slide back together. Um, in other words, if it's a real value signal, x of t, are orthogonal when the contribution of one to the other is 0, or c equals 0. What makes it incredibly, if you go back to the definition of C, right? So it had the product of the two signals, right? The energy of x of t would not make sense to make it to be 0, right? So the only way that ratio of those two integrals is 0 is the numerator is 0. So for um, two signals, x of t and g of t, are orthogonal over that interval if and only if the integral of the product equals 0, right? Which is a remarkable result. Okay, it's easy for us to determine if two signals are orthogonal or not. All we have to do is do the product, integrate over our interval, and if that comes out to be 0, they are orthogonal to each other. Now, we can generalize this orthogonality concept to complex signals. Again, if the signal g of t um, that we're trying to approximate with the function x of t over our interval, right? Uh, Both the coefficient and the error function, those functions are complex. If that's the case, then our coefficient c and our error function will also be complex, right? And then it just so happens that now we have to use the absolute value of x of t because it's complex, right? To determine the energy, right? And we will also need to calculate the energy and the error signal. I'm sorry, this should have been e sub lowercase e here. The energy and the error signal is the same thing, right? Because it's also complex. We take the magnitude of the error signal squared. Um, okay. Now, after some mathematical processing, right? So we do some derivations. We end up with c equals 1 over e of x, right? Integral of g of t, and now we have to do the conjugate of x of t. Now, if my pen would cooperate just a little bit, you just to sort of um, remind you guys what a complex number is, right? So if I have a variable c, which is complex, is going to have a real part a, let's say, plus an imaginary part b, where j is the imaginary operator. So the conjugate of z, which we use z, and we'll put a little asterisk, would be a, and then you negate, right? So you would say a minus jb, and the pen really doesn't want to cooperate today, but hopefully you guys get the idea. We can also define the requirement for orthogonality of complex signals x1 and x2, right? And it's just that all you have to do is you multiply one times the conjugate of the other one, and if it comes 0, um, either way, you can either make x1 or x2 the conjugate, and when you multiply it by the other signal, if the integral comes out to 0, that's a sufficient condition to say that they are orthogonal, right, in a complex sense. We can prove that the energy of the sum of two orthogonal signals is the sum of the energy of the two signals. So if we had two signals, x and y, um, we can and we say that the signal c equals to the sum of those two signals. The energy of z equals the energy of x plus z. You might think, oh, that's a natural occurrence of it, but if you have to go back to through the math to actually prove this, right? And I believe the textbook makes an effort to do that. But this is again one of those things that even though you think it's a given, not necessarily, right? So this result can be extended to any number of mutually orthogonal signals. So as long as x and y are orthogonal, you can actually say this, right? And the reason is that because they're orthogonal. Remember, going back to the vectors, right? One does not contribute to the other, and vice versa, right? It's like there's no coupling between them. Okay, so they're totally um, not related to each other, have no coupling between them, or there's no kind of correlation, which is our next topic, right? Let's talk about correlation of signals. Um, what if you had two signals, and in general, you don't know where they came from, what they are, but you want to know how similar they are, right? Uh, this sim this measure of similarity is what we know as the correlation coefficient, right? And we use the letter Greek rho for that. And you'll find that in almost everywhere with it that we refer to the correlation coefficient. Note that the correlation coefficient is has a range between -1 and 1. It's so in other words, the magnitude of rho, correlation coefficient, is always equal or less than 1. That's the only range of acceptable values. And again, looking at it in terms of vectors, if you had two vectors and they align perfectly, right, their correlation factor will be 1. If the two vectors are aligned, but in different directions, right, they're going in different directions or pointing in different directions, either way you want to look at that, that means they're opposite to each other, and therefore the correlation factor is -1. It's not 0, it's -1. They're opposite to each other, right? Now, if the two vectors are orthogonal, that means that none of they're not coupled in any way, right? Now, our correlation factor is 0. Okay, that means there's no relationship between the two signals, right? So if it's two vectors, they're actually 90 degrees from each other. Okay, so you cannot calculate the uh, component of one vector along the other because it's 0, because they're orthogonal to each other. Um, so for convenience, we consider signals over, let's say, the entire time. Now, again, we started off by saying we don't know where these signals came from, where or what they are. We just don't know. So in general, we're going to talk between -infinity to +infinity. So we're not going to restrict ourselves to an interval as we've been doing. So we can come up with uh, a correlation index for those kind of signals from minus to +infinity, right? But the, we should always have rho be an index that is independent of the energy of the signals, which is, again, going back to the vector analogy, if the two vectors are pointing in the same direction, they're actually the same vector eventually, right? You can think that they are going to go through the same set of points as they go towards infinity, if you will, right? Because they're just pointing in the same direction, right? Um, so we need to normalize our two signals to have unit energies. Therefore, some bit of hand waving here. We end up with rho being 1 over the square root of the energy of the product of the two signals, and we integrate the two signal product from -infinity to +infinity. Okay. Now I can take any of these functions and multiply it by a constant, and still, right? If you think about it in an analogy of the vectors, it doesn't matter, right? It's the two vector. I can multiply it by uh, any kind of constant, and I should still get the same correlation factor. And we can extend this to complex signals. You just have to multiply, take one of your signals and um, put the conjugate inside the product of the inside this integral. Okay, let's do an example because I find that an example here is sort of very telling. So let's start off by saying that you have a signal x of t, right? Notice that it's nothing but 1 between 0 and 5 and 0 everywhere else. So um, makes our life a little bit easier because we only have to worry between 0 and 5 and not between -infinity to +infinity. And we have 6 signals, and we want to know what the correlation factor is between x of t and those 6 signals. Now, right off the bat, right, if you look at signal B equals x of t, so they're equal. So whatever mathematical procedure we do, we should see rho equal 1, right? And then the rest of them, let's see what we get. Um, if you follow the example in the book, all right, the first thing to do is calculate the energy of E of x, which is x squared, integral between 0 and 5, but that's 1, right? So if you integrate from 0 to 5, and you end up with 5. Okay, nothing to write home about. And you could have done that by inspection, by the way, because this is a rectangle, right? The integral is the area under the graph. And in our case here, 1 times 5 equals 5, right? Um, and we need to calculate the energy of the rest of the signals, right? Because we need that to calculate the our rho value. So EG of 1 is the same as E of x, so that's 5. Then the next one is 1.25, etc., and so on, right? Um, and again, you guys should convince yourself that this expression is correct for, I think we're doing G of 5, right? G of 4 and G of 5 are exponentials, so you guys convince yourselves, okay? Um, and then E of G is a sine wave from 0 to 5, and it comes out to an energy of 2.5. We have everything that we need to calculate our value of rho. So actually all of this that you see here, right? All of these factors that we're talking about here, right? All the way here. All of this stuff is rho. Rho equals that, right? 1 through 6, okay? So, and so a few more comments about this. So if I look at the first one, sure enough, it came out to be 1, okay? And then the next one, we said that it doesn't matter what value, if we multiply by a constant, right? We actually said that. You can multiply by a constant and it shouldn't change the correlation factor. And G2 is nothing but G1 multiplied by 0.5. I don't know if you guys have realized that. And notice that the correlation factor still comes out to 1. G3 is nothing but G1 but multiplied by -1, right? So that's kind of in the totally opposite direction. So rho came out to be -1. So they're opposite to each other, right? And we see that, right? One is sort of +1, the other one is -1, so they're kind of opposite to each other. Um, with the exponentials, you can see there's some likeness to the original x of t, but because of the exponential, they're not really, it's really not a coefficient. You're multiplying by e to the minus t to the t over 5, for example, right? Um, so the correlation factor is not 1, but it's not 0 either, right? But 0.96. And then the next one is 0.62. You can see the exponential dropped so much faster. Now the sine wave is rather interesting. You would have thought that there was some correlation because there's energy on the plus side, but guess what? There's also energy on the negative side. And by the time you look at this signal and you compare to that, there's really no relationship to them. And actually, it turns out that sine of 2 pi t is orthogonal to our x of t because the correlation factor came out to 0. Okay? Um, let's talk about correlation functions. And this is used a lot in communication systems, this whole concept of correlation. Um, oops, sorry, I skipped a slide. Didn't mean to. So let's say we have two signals, g of t and z of t, as shown in this figure. If you were to apply a rho to this, it would come out to 0. And the reason is when you look at it, they're in different time slots, if you will. They happen at different instants of time. So it's kind of naive to think that you can always have in the real world signals that happen at the same time, even if they're equal to each other, right? So signals don't always overlap. But if you look at this carefully, these two signals are pretty much the same signal, right? With a time difference. Oh, wait a second. All this is we learned earlier and the first part of this lecture that a signal is delayed if you just subtract a certain value, in this case, capital T, right? These two signals are the same. It's just that the one in B here, right, is delayed by T seconds, capital T seconds, right? So we need to accommodate for this case. And the way we do that, right, when you have a relative time shift is we come up with a function we call psi, and we call that the cross correlation. So the nice thing about it is this function psi is actually a function of tau, where tau is the delay. So we're replacing capital T. We've been using capital T all the time. So we're going to replace it for tau to kind of make ourselves think it's more generic. But this is the expression, right? You can use either one. And the idea here is to be able to um, not only determine how much correlation you have, but you also want to be able to determine the delay, right? So you look at two signals, and for those of you who have done convolution before, you just the equation is very similar to convolution, except that uh, the second function in convolution, you actually create a mirror image of it and then slide it across. In correlation, right, and cross correlation, we do the same thing, except that we don't have to mirror the other function before we move it across. Okay, that's the same thing here. You're trying to do that, and by doing that, you can actually figure out what the delay is, and that's how they calculate these cross correlations. Okay, so you start moving tau different values, and what you're doing is you're sliding the function, and then when it becomes psi becomes a peak, you identify that peak, you say, this is how much the delay is, and then you can figure out how correlated the two signals are. Okay. Um, so I have an octave example for you guys. So let me go ahead and transfer over to octave to do this. So what we wish to do in this exercise, right, is to um, figure out what's the correlation between our x of t, which is this first function here. Hopefully you guys can see my marker, and the other five signals, similar to the example that we just looked at, right? So switching over to octave, let me go ahead and I need to go open that. Let me go to the right folder. And that folder is, let me go to my Valencia folder real quick. And this is example number 5. It's for those of you taking the course, is in uh, already uploaded to Canvas. If you ever look at the example in the textbook, again, the textbook has in section 2.10 has a lot of extra equations for plotting. I took those equations out because I want to focus just on the calculations of the correlation factor. Okay. Um, uh, and I think that that's kind of the best thing for us, right? So the procedure is very similar to what we've been doing for a while now. Um, we calculate what the time increment needs to be, what the duration is, then we come up with a vector for our time values, right? That's what happens between lines 4 and 5. Uh, then between lines 8 and 13, what we're doing is we're just uh, um, giving the functions, right? We're creating all the vectors for each of the functions for x and g1 through g5, right? So these are all our signals, if you will, right? Notice how we create this first our x of t, right? We use the unit step function that we talked about in our last class, right? And if you look at it carefully, it says the unit step minus unit step at t minus 5. So you remember unit step starts at 0 and goes from 0 to 1, and it would stay at 1 forever, except that in this case, we then go minus, which is in, we invert the unit step, right? Now it's minus 1 at t minus 5. So it's like taking a unit step and subtracting the unit step at t minus 5, and that's how we get our square wave. And I'll let you guys kind of figure out the rest of them. Um, we can calculate the energies of the signal. That's what we're doing in between 19 and 24 of all the signals. Um, and it's nothing but the sum. And notice how we use the conjugate function, right? to make this generic in nature. So this code is generic in nature, and our functions right now are real functions. But if they weren't, and they were complex, this would take care of it, right? So this code takes care of the general term. And then the first term, whenever you look for the correlation between a signal with itself, we call that the autocorrelation instead of the cross correlation because it's a signal with itself, right? And there's reasons to do that, right? When you do the correlation of a signal with itself, you know you're going to get rho equal 1, but you also get the delay, right? So if there's a delay between uh, the signal and where you're measuring the signal, you can figure it out with the autocorrelation in general terms. So not in this code, by the way. There's no delay that we're doing in this code. We're just looking at the magnitude of the uh, of rho, of the correlation, and then we do C1 through C5 or lines 29 to 30 as the other correlation factors. And if you run this, you get the oh, sorry, I need to go. I need to change this to the load path. Sorry. There we go. Let me do that real quick for you guys. Um, all right, now it should run. So what was happening is I was not pointing to the right folder and it couldn't find US step. It's actually what I was complaining about. So now when you go to the um, command window, you'll see what the autocorrelation and the correlation factors is. And it's quite interesting to see that C5, right, as about 0, right? I know e to the minus 17 that may not seem to 0 exactly to you guys, but it pretty much is. So what that tells us is that x of t and g of 5 of t are orthogonal, which we kind of saw from our example a little bit earlier in the lecture. Okay, so let's go ahead and go back to the slides here. Okay. So we like to talk about orthogonal signal sets. So we do this because we want to decompose a signal as a sum of orthogonal signals or a set of orthogonal signals, right? So let's say we define a set of signals, x1, x2, all the way to xn of t, right? And let's say it's over a time domain, or sometimes you might want to call it a time period, theta, right? Which goes from T1 to T2. Okay, so essentially, if we take a signal x of m, right, and we want to find a set of orthogonal signals, all of our signals, doesn't matter which ones they are, right? I should be able to take x of m, right, whatever the signals are, conjugate of my x of t, the signal of interest. They should, when I do this, they should all be 0 unless m equals n. And I do apologize, there is a typo on this slide, and this should have been x of n here. Okay, I'll be sure to correct that and re-upload it to Canvas. Okay, so it should have been x of n. Okay, so that when m and n are equal, you get some kind of value. Okay. If all energies have equal value, E of n equals, then the set is a normalized, and it's called an orthonormal set. Okay. But that's not a requirement for them to be an orthogonal set. It's just that at that point they're orthonormal. And having an equal to 1, kind of nice for some calculations, right? You can always normalize it, right? By dividing whatever x of n you have by the energy. And if you normalize them all, then you get an orthonormal set. Okay, now getting back to approximating our signal g of t, in an interval capital T by n mutually orthogonal signals or an orthogonal set. So essentially what we want to do is this, right? We want to say g of t equals an expression like this. So notice all the coefficients, right? So essentially, if this is a real function, we can say that we want to sum from n equals 1 to n all these Cx orthogonal signal set, right? And we can always look at the energy in the error signal, is right, and we could try to minimize that, and we already know how to minimize that. So we looked at this before, but this is sort of a generalized expression, mathematical expression for it. But it's pretty it's the same as an expression that we looked at before. Again, this is just generalized here for complex signals as well. Um, and what kind of name do we give this? We actually call this the generalized Fourier series um, of G of t. Uh, and it's with respect to a set of orthogonal signals xn of t, right? So when we have a set of signals such that the energy tends to zero as n goes to infinity, we say that the set of our orthogonal signal is a complete set, right? For the class of signal g of t, right? And so we can call these x of n, they call them by a lot of different names. You can also call them basis functions or basis signals, okay? All right. Now, let's talk a little bit about Parseval theorem. Recall I mentioned earlier that the energy of orthogonal signals, if the signals are orthogonals and you add them up, you can also, uh, if the signals are orthogonal, you can add their energies, right? Therefore, the energy of a generalized Fourier series is the sum of the individual orthogonal components, right? So you end up with a function that looks like this. And this function is credited to Mr. Parseval, who actually proved that this was correct, right? This is a function that the total energy of G equals the energy of the sum of its basis functions, right? Okay. Um, when it comes to Fourier series, there's all kinds of orthogonal signals that we can use as basis signals. Here, the book mentions a few. For us, we will concentrate on trigonometric and exponential sinusoid functions. Okay, the rest of them very interesting, but it's beyond this course, and we just mentioned them here for completeness. Now let's talk about the trigonometric Fourier series. Let's consider real complex periodic signals, right, with some period t0. Um, talking of basis signals that we are going to use here are actually trigonometric signals. We're going to use sines and cosines. Okay, so we're going to end up with a basis signals. We're going to have some kind of constant, and then cosines, right? And they are going to be a function of this n value, and the same thing with the sine function. Also, you can see that they're kind of a function of the m value. Uh, the n or nth value or n omega 0, we call that the nth harmonic. So now we're beginning talking about harmonics. So if you have a frequency of 100, right, the second harmonic is 200, the third is 300, and so on and so forth, right? So as you increase n, which n is an integer, right? You could talk about it in terms of radial frequency or normal frequency, right? You can talk about it in hertz or in radians per second. It doesn't matter. We'll still call them harmonics. Okay. It turns out that if n equals 1, we actually call that the fundamental tone or the fundamental frequency. Um, Notice that there's a constant term. That's just what's represented by this one here. That is the zeroth harmonic or harmonic where when n equals zero. That is commonly referred to as a DC component because that's what it actually is, a DC component. Okay, so if you have a signal and you're trying to represent it with a Fourier series, that first term is actually the DC term of the signal. So in a trigonometric Fourier series, we can do a little bit of sort of coming up with a compact representation of it instead of always showing all the cosines and stuff. We can actually sort of make it in a compact way because if you look at the expression and we replace that one with a0 to make it more generic, and then we call all the coefficients a1, a2, and there's kind of a typo here. Again, I'll fix these slides and I'll re-upload them to Canvas. There should have been a 1 here, and then there should have been, and there should have been an A2 there. Um, and so, where, okay. So again, A1, and this is A2, and so on and so forth. And again, I'll update the slides. So you end up with an expression like the one I have boxed here, where g of t equals a of 0 and the sum from n equals 1 to infinity of cosine and sines multiplied by the a and the b coefficients, right? And this is for a periodic signal, okay? So the Fourier coefficients can be calculated, right? Again, a little bit of that hand waving here, using these expressions, okay? I know at this point it seems, wow, we're going to be evaluating a lot of integrals. Um, uh, you'll see it in a little while. We're going to actually go back to Octave and do that. And many courses, at least when I took it, when computers weren't as prevalent, professors would make us calculate these all the times. And if I wanted you guys to calculate it, and those of you taking the course, I would make it a small n, right? We don't have to calculate it for all n's. It's just make sure that you guys can calculate it. But many times, we're just looking for an expression, right? A of n equals and some kind of an expression, okay? And we'll see that in an example, I think, shortly here. There is an even more compact way of showing the Fourier series, and it comes down to this identity, right? If you have A cosine something, B cosine something, you can express it as C cosine of an argument plus a phase, right? And then the C of n, or the magnitude, this is what it would be. It's the square root of an plus bn, kind of no surprise there. Plus the phase, which is b, again, minus bn over an. Again, no surprise there, hopefully for you guys. With the DC term, C0 equals A0. Again, so this is what the compact form looks like. It's a little bit easier, more kind of pleasing to look at, if you will. Here's an example. So again, we're going to start off by taking a chunk of a signal, g of t, and making the assumption that it is periodic. So we're going to take between 0 and pi, and then we're just going to repeat it to come up with our periodic signal, right? So in A, you have the aperiodic signal, and in B, you have the periodic signal, right? And then in this example, just to refresh your guys' mind, omega 0 is nothing but 2 pi over t0, or 2 pi times f0, where f0 is 1 over t0. And for our example here, um, t0 is the period, right, which is pi. So f0 is 1 over pi hertz. Um, and if we want to determine the Fourier series, then we apply the integrals as we did looked at earlier, right? So A0 is when n equals 0, comes out to 0.504. So there is a DC term in here, right? It turns out, but see, the signal doesn't go to 0. So if you look at the average of this signal, right, it's around 0.5. 0.504 is the exact number. And then here's what I was saying earlier, right? I'm not going to ask you guys to evaluate this integral over and over. What we would like you to be able to do is, and again, convince you guys have to convince yourselves that this integral evaluates down to this expression between 0 and pi, of course, right? And the same thing for b of n. When you evaluate the integral, you end up with an expression like this. And then this expression is actually a lot easier to evaluate for lots of n's, right? And at this point is where I was saying, yeah, at this point, just go to Octave or MATLAB and evaluate a are your a of n's and b of n's, and you can come up with a series and look what it looks like. It would be, in this case, an interesting exercise, right? Once you take all your terms, right, and calculate your c of 0, remember it goes a of 0, c of n, and all your phases. The phases came up with a really nice expression. Actually, the magnitudes to this is not too bad. Okay. Again, convince yourself that that's the case, right? You end up with these two expressions, and then g of t ends up being something like this. And this is easily programmed inside of um, Octave or MATLAB between 0 and pi. And by now, I presume you guys know how to do that. Okay. And a nice experiment would be to change, notice how it says n equals 1 to infinity. Well, I would go n equals 1 to 3, to 5, to 10, and see what you what you should what you should see is the more you increase n, the closer your function or your plot, if you're plotting it, begins to look like this. Okay. And then you can plot it beyond pi, right? Because this expression, even though we extracted it between 0 and pi, because we know that the function is periodic, if you continue to extend it, it should work out. Okay. Um, and everything that I was saying about periodic signal is on this slide. So I'll give you a minute to go over this slide. Just go ahead and read there. So the bottom line is, even though we're computing the coefficients A0, AN, and BN, right, we may use any value of T1. You can start T1 for the integrals wherever you want. Pick a place that's convenient for you, right? Depending on your signal. You always pick a place that's the most convenient for you. We know it's going to be periodic, so at the end, our Fourier series, right, of our signal is going to apply to the whole signal, right? Okay. So here's another example. Here's a square wave. It has period pi. Notice how, or here it goes from minus pi over 2 to pi over 2. So this is a width of pi. Sorry, I said the period wrong. And this, hopefully this doesn't happen to you guys. So notice that the signal is actually periodic, and it starts from here and it ends here, right? You can look at it so many different ways. You can say, oh, the signal starts here and goes up to here, right? From here to here, right? Uh, okay, more or less. So, and that is 2 pi. Okay. Um, and if you calculate the Fourier series, you're going to get something that looks like this, right? And you can see what the magnitude, right, of the different, actually I shouldn't call it magnitude, call it amplitude. So I'll just make a quick, so I normally talk of the amplitude of a signal, amp, geez, this thing really doesn't want to cooperate today. So we could talk about the amplitude as being some kind of magnitude. It really doesn't want to work today. Um, some kind of magnitude of A and an angle of A. That's what the amplitude is, where the magnitude is the absolute value, and the angle is whatever the angle comes out to be, right? Um, so here is the calculations. Again, A of 0, n equal to 0 comes out to 1/2. That's your DC term. If you go back to the graph, you'll notice, right? Here it is 0.5. And then the rest of the values as you calculate it. It turns out that for n equals even, everything is 0. For n starting at 1 and every fourth number, it's 2 over pi over n. And then for every fourth harmonic starting at 3, right, it's minus 2 over pi over n. And all the b's came out to be 0. Okay. Again, you should be able to convince yourself of this. Look through, um, look to solving the integral, and you'll see that that's the case. What ends up happening is, in the case of sine, you end up evaluating sine at either pi or minus pi, right? And then sine of pi or minus pi is always 0. So you end up with a function after you go through that looks something like this. Now you'll notice that it seems like all of a sudden these coefficients have this negative value. And in theory, when you go back, all right, everything should end up being a positive, all these coefficients, the C coefficients, right, uh, in the expression for the Fourier series. And you can think about it as minus cosine being cosine of x minus pi. So what really happens is all those coefficients have a phase, right, of pi, and when you minus pi. When you put that in, then you see they all end up with um, some of them end up with a phase of minus pi. That's what the textbook is trying to do. If you just plot them as we did before, and look at it in this plot, and we call this plot the frequency spectra, or the spectrum of the signal, right? And for those of you who have ever used a spectrum analyzer, this is the exact same thing that you see on the spectrum analyzer. Um, if you just leave the positives and the negatives, then you can kind of see you get a plot something like this, right? So from this plot, you can identify which of the terms have a phase of minus pi, which is the ones that are negative, right? Or if you think of these as um, something that's pointing either up or down, the ones that point down are the ones with the pi phase, okay? Um, so the amplitude and phase of periodic signal, that's what I was calling the amplitude a little earlier, right? So um, this spectrum is what is shown here, which is the spectrum. So the spectrum tells us at a glance what is the frequency composition of our signal. Or in this case, because we're using a basis function that are trigonometric, it tells us what the sinusoidal components of WT are. That's why we like to look at this. The frequency spectrum provides sort of a different view of your signal. You're viewing at your signal from the frequency domain, not the time domain, right? So the time domain is what you see on an oscilloscope, right? When you look at the sine wave, you see the sine wave going up. The same thing with the square wave. If I were in this instrument called a spectrum analyzer, I would be looking at the frequency spectrum. And if I would put in the waveform that we were just looking at, this is what I would kind of expect to see. So the book goes on to call this a dual identity. I have a little bit of a concern with that. It's the same signal. You're just looking at it from a different point of view, right? So uh, you just have to kind of think about a signal, think about it as in 3 dimensions, where one axis is time, right? The other axis is frequency, and the third axis is let's say the magnitude, right? If you look at it that way, you can see that you can rotate this 3D plot and see different uh, aspects of the signal, but it's always the same signal. It's not like it has two identities. I find that concept a little bit strange to handle. It's the same signal viewed from a different domain, either a frequency domain or a time domain. Here's another interesting example and property of our impulse function, right? So let's say I create a periodic signal that's made out of all these impulses, right? If you go through the trigonometric Fourier series and you do this, right, and you figure out what is omega 0, right? Um, and the period of the signal is, by the way, is t0. Notice that it repeats the impulse function every t0 seconds, right? Um, you can calculate a0 and an. Again, this becomes fairly simple because if you remember one of the property, the sampling property of the impulse function, right? It is only when you do the integral, right? Because this is one only at 0. This whole and the integral of it is from minus infinity to plus infinity is 1, right? This whole thing, it doesn't matter that the interval is less than minus infinity to infinity, it's still 1. So 1 over t0 is the result. Same thing in here. Remember the sampling property? So you only have to evaluate this at wherever the impulse function is valid, and this impulse function is only valid at 0. So cosine at t equals 0 makes the whole argument of the cosine 0, cosine of 0 is 1. So the whole integral, then you have 1 times the impulse, you end up with the impulse. Again, the integral of the impulse, right? Doesn't matter, the interval is 1, and you end up with 2 over t0. Okay, that's how fast, and hopefully you guys followed, and there's my evidence of proof. Kind of the same story for Bn. It comes out to 0 because again, sine of 0, this argument is going to go to 0, and sine of 0 is always 0, so the whole thing becomes 0. Okay, so and then this ends up being the Fourier approximation of our signal made out of all these impulses. And wouldn't you know that this is probably this is the only signal that the time domain and the frequency domain look so similar. They're not equal, they look similar, right? So you have all these impulses, all these vertical lines, if you will, and you have the same thing in the frequency domain, right? And if you do 1 over t0, 2 pi of that, that's where they all land on the frequency domain. Quite an interesting and remarkable result. We can do the Fourier series with an exponential. Now, let me see. My pen will cooperate for just a little bit here. It really hasn't not wanted to do that today. E to the j theta is the same. It equals. This is called Euler. Euler spelled E U L E R. It's nothing but e to the j phi. If you do that, it comes out to cosine of phi plus j sine of phi. Um, Now, if you had e to the minus j phi, that would equal, this is all from Euler, right? Cosine of phi. Notice that the potential now is negative. Minus, here's where the minus, the negative shows up, sine of phi. Okay? And we'll be using this identity quite a couple of times during the course, so I took the time to explain it. But if you haven't never heard of it, please look up the Euler identity, and that'll explain it for you. Okay, so if we want to use this exponential, as our basis function. Again, we have to do the integral, right, over the period of time right here. And what we'll do is, um, thanks to the properties of exponentials, you end up with e to the j m minus n. And then the function is, the result is quite straightforward. If m not equal n, this is 0, so they're orthogonal. And when m equals n, the value comes out to t0, right? Hence, the periodic signal g of t using our basis functions, um, these exponential expressions as our basis function, comes out to a constant d sub n times our basis function, where d sub n is defined by this expression. And again, d sub n is complex valued, or is a complex value. Okay. Um, Here again is a quick exercise, the same one kind of that we did a little while ago for the trigonometric Fourier series. And again, when you go through, again, convince yourselves that this is what the n ends up being, right? 0.5, 1 plus j for n, right? That you guys have to convince yourselves of that. If you remember a little while ago, we did say that the DC value was 0.504. It should come out to be the same DC value. So D0 equals C0, or A0, excuse me, from the Fourier series. Okay, that should always be the case. And if you break down e to the j values here into sines and cosines, as I did before, you should end up back to the trigonometric Fourier series, right? So the two are related, and that's why I talked about Euler, right? So that's why I was saying that Euler, e to the j phi, right? That I was talking about a little while ago. Okay, so to complete the example, right, we end up having that the dn values for this square wave, right, for this square wave, end up being 1 over n pi sine of n pi over 2. Okay? And again, I'll leave you guys to walk through the integral here. But and again, we did this one also for the Fourier series. And again, you guys need to convince yourself that the two kind of give the same results, right? Once you express it as a function. Um, the nice thing about the D is it's really easy to sort of do these plots as well as we were doing with the A's and B's. Um, so remember that I just mentioned a little while ago that D0 equals C0. Um, and observe that in this case, the magnitude of the dn equals the magnitude of d of minus n. What that is saying is the minus one, right? So we have dc around 0.5, and then these two will be the same. And anytime I go like for 5, I look at minus 5, again, they have the same magnitude. So when you look at the minus n one, the same thing, let's say minus 7 and plus 7, right? They're the same. That's what this is saying. And the d of n's are equals c of n's over 2 from the Fourier series. Um, let's go ahead and look at this octave example. So I'm going to go, and where is my octave? Right here. Okay. So for those of you in Canvas, again, this is chapter 2, exercise 5, the FS function of transfer Fourier, right? Um, and, and again, this is not really earth-shattering, and you can follow this. I do express the J operator as square root of -1, which is by definition. I'm going to use A and B from pi over 2 to, and A is minus pi over 2. we are going to use something called a numerical integration. There's a quad function that you can use to do numerical integration, and that's what we're going to be using today, right? So first we create our rectangle. We need to create our rectangle. So I'll let you guys again. We've done this numerous times, so I won't spend a whole lot of time going through that. And then, but I will spend a little bit of time talking about how we calculate, for example, D0. Now, this is, if you've never seen this, this is a way to tell Octave and MATLAB, hey, I want this function is going to be evaluated at a value of t. So whenever I call func, stands for function in this case, that's what I wanted to evaluate. I wanted to evaluate the rectangular function at this value of t. And the rectangular function is a function that I have already defined. Um, Let me go in. I can open it. It's not earth-shattering, right? Again, this is already uploaded into Canvas for those taking the course. And it's nothing but the sign of the function, right? So it just creates a rectangle between zero point 0.5 and minus zero point 0.5 and zero point 0.5, a rectangle of uh, of magnitude 1. That's it. Okay, so we are then going to go and follow our expression for to calculate d, right? So we calculate, did I miss D0? No, this is D0, sorry. So we are going to go ahead and say 1 over t quad. Quad is evaluating uh, that integral, right? And what is it going to integrate? It's going to integrate the function that we define, okay? It's going to go between a and b, and you have to specify a tolerance. So it's going to use some kind of recursive, some kind of thing, and you have to tell it when to stop, when is it good enough. And I believe we defined the tolerance as 1e to the minus 5, which again, arguably is a small number, okay? And again, you guys can experiment with that, see if you see any differences. Um, then we calculate the d of n's for the positive side for n equals 1 to capital N, right? So we're going to calculate those. Here, the function is a little bit different. Now, we said that in general, d of n are complex because this applies to complex functions. Now, this is a little bit different when you go and look at it in the textbook, because what I found is the quad function does not like complex functions. So what I did is I broke it into the imaginary and real part of the function. So this is why you see this is the real part and this is the imaginary part, right? And then at the end, what I do is I just add them together. Okay, add the real and the imaginary part. So the event in general terms could be complex. Turns out we're dealing with real signals. I could have gotten away without doing that. I could have just done these two and get away with it. But it's only because my function is real. But I felt it important to show you guys that you can do complex signals. It's just that you have to do a little bit of more work. Okay. The same thing is happens from between minus n and minus 1, right? And that's what this part of it is, right? So we're going to evaluate that. And the rest of it is just some plots and things. Again, all this is already on Canvas for you guys taking the course. And if you go ahead and run this, sorry, the function ended up off screen. But and if you go back and you look, you'll see that here is our rectangular waveform on the top, and then at the bottom you see what the values of the d of n's are, right? And I didn't look at the magnitude. I'm looking at the amplitude, right? I clearly specify the amplitude, and I try to make um, the explanation of what I mean by amplitude and magnitude a little while ago. Okay. Let's get back to the slide so that we pretty much go ahead and wrap up today's lecture. Okay, so we talked about this example and that the fact that we are using the direct integration method inside of Octave. Parseval's theorem, again, it applies here to both the trigonometric Fourier series and to the exponential Fourier series. So if we were doing Parseval's for the trigonometric Fourier series, this is what g of t would look like as we defined it earlier. And then what Parseval tells us is that the power of g equals the sum of the powers of the different components, and that this is kind of what you get, right? So you just have to do 1/2 of CNN squared, add them all up, put the square of the DC terms, and you have your powers. This is directly falls from Parseval's theorem, okay? And the same thing for the exponential, okay? And that'll be our lecture for part 2 for our lecture today. See you guys in a future lecture. Thank you.